Okay, so I'll be using the same region S described in the previous questions, where it's a region bounded by y equals to square root of x and x equals to 4 in the first quadrant. And this time, we'll try to rotate this around, not around the x-axis or y-axis, but on a different vertical or horizontal line. So let's try with y equals to -1 first. Y equals to -1 would be, here's -1, and you have that dotted line. And imagine that you're rotating this region around this so that eventually your picture will be something like that, but these are dotted lines. That's also dotted. That doesn't really exist. It's like that. Okay. So hopefully that makes sense. Although I explained both the washer method and also the cylindrical shell method, we'll try to stick with the washer method. So let's try to calculate this volume by our favorite formula. Anything is sum of its parts, right? Where this dV is ambiguous, it depends on, the meaning of dV depends on how you split this into small pieces, okay? And by doing washers, I mean I'm trying to cut it in this direction so that the cross sections will look like a circle with another circle in there, just like this. These are circles. You're viewing from the side, that's why it looks like an oval, but these are actually perfect circles viewed from the sideways. And we're trying to add these to get the entire volume, except that this by itself has 0 volume, so we need to make it to have an infinitesimal volume. How do we do that? How do we make something that has a small volume? There was a word I used. You thicken it. Yeah, you thicken it perpendicular to the face, right? You thicken it. Okay. And this is actually quite important. You have to know which direction you're thickening it. So in this picture, when you rotate this, this cross section is actually perpendicular to this board, right? And when you thicken it, which direction are we thickening? It's this way, right? We're thickening it like this. So what is this? dx.
X1 and X2. And then
Yeah,
dx is like in
dx is an infinitesimal increase in the x coordinate, right? So this here will be dx. So dx is going to be our thickness that we attach. Then the volume of this object, which we'll call it as dV. dV will be the area of the big circle. Remember, the area of the circle is pi r squared, right? Minus the area of the small circle, where big R is the radius of the big circle, small r is the radius of the small circle, and we thicken it by dx. So that's going to be our dV. And we write it now in this format. Let's factor the pi out so that it looks like big R squared minus small r squared dx. Can you tell me the bounds now? It's the x value bounds, right? In the picture, x goes, yeah. Here x is 0, here x is 4, right? So x goes from 0 to 4. Okay, this is still not ready to integrate because we need to know capital R and small r, right? We need those to be a function of what? Should it be a function of y or x?
Since we have dx.
Dx means that I need these to be a function of x. Okay. Right. And as a function of x, in this picture, this is your big R, right? And this much is small r, right? You see that when you rotate this around, this length will be your big R, and this will be a small r, right?
Small r is from y equals to 0 to y equals to -1.
That's correct, yeah. So I guess this is what I want to say. Big R is from y equals to -1 to y equals to square root of x. You start from this dotted line and you go way up till this. You go up, up, up until you reach this curve y equals to square root of x. Right? So it's from this to here. Small r is from y equals to -1 to y equals to 0. And I'm writing this in the order where you go from small to big. Okay? So the numbers go down as you go down, right? And numbers increase as you go up. The y coordinate increases as you go up, y coordinate decreases as you go down. So I'm trying to go from lower one to the upper one. How do you actually measure the distance though? Distance, yes?
You just minus y2 minus y1.
Yeah, you subtract. You subtract to find the distance between two places, right? So you have r, therefore, as square root of x minus -1. And we think of this as like top minus bottom. So I guess that this is what I'm trying to say. When you have dx, your thickness is the dx, and these should be y coordinates. And whenever you want to find a distance like that, that's like top minus bottom. If this was dy, then you're going to be looking for the differences in the x coordinate to get capital R and small r. So in that case, you'll be doing right minus left. So we do top minus bottom, and because negative of -1 is positive 1, you have square root of x plus 1. How about small r?
Would be the
Top is 0. Right? Bottom is -1. It's positive 1. And now we're one step closer to getting the answer. It's integral from 0 to 4. You can pull the pi out. And capital R is square root of x plus 1 squared minus 1 squared dx. Now you can compute this. This is ready to be integrated, right? If you square this, it's square of square root of x and square of 1. But there's something extra, right? What is that extra?
1 square root x. No, 2
So
square.
a plus b squared is a squared plus b squared plus
2 x.
2ab. 2ab, so it's twice of this times this, so 2 radical x comes here. And minus 1 squared. These two cancel. So that's the integral of 0 to 4 of x plus 2 times x to the 1/2 power dx. Whose integral is 1/2 x squared. Let's see, for this one you have to add 1 to the exponent. 1/2 plus 1 is 3 over 2. Put the reciprocal as 2/3 times 2. And then you plug in 4 and 0. And pi. 16 times 1/2, that's 8. Square root of 4 is 2. 2 to the third power is 8. 8 times 4 is 32. 54. 56 over 3 pi.